Okay, so welcome everybody to this AJS seminar. Today's speaker is Laura Meneghetti, and she will talk to us about the use of convolutional neural networks for image recognition and object detection. Thanks, Laura.
So good afternoon to everybody. Thanks, Francesco, for the introduction, and thanks also to Sara for organizing these seminars. So, as Francesco told you, my topic of my talk will be about a reduced approach for convolutional neural networks for the problem of image recognition and object detection. So my project is in collaboration with my supervisor, Gianluigi Rozza, and my co-supervisor, Nicola Demo. And my PhD is also in collaboration with Electrolux Professional, a leading company in the field of professional appliances. So before going into deep into the topic of this reduced approach, I will introduce you the framework and the motivation that has brought us to the construction of this reduced approach. So, first of all, the goal of my project was about building a convolutional neural network that is able to recognize and detect the position of different types of crockery and cutlery that are placed inside a rack in order then to be placed in a professional dishwasher. So as you can see from the picture, we have this convolutional neural network that for now only to think that this convolutional neural network is an algorithm that is able to solve this task. Then we will see some more details. And so what you have is that you have this algorithm that is able to take in input an image like the one that you can see here. So you have the rack with all the dishes, and you want to have in output the same image, but around each dish, you want to have this green rectangle that are telling you where the dishes are detected and then are located. And then you want also the correct label associated with the object. So in this case, we have as label dishes. I want also to mention that for all the things that we have done, we have used PyTorch, and in particular for the code of the reduced approach that I will describe you will soon be available on Snitters, so on the GitHub page of the MATLAB group. Let's see which are the fundamental steps that we need to follow in order to implement such an algorithm. So first of all, we need to have a dataset. Here you have basically two different choices. You can decide to use one of the datasets that you can find online and that are usually used as target dataset. So maybe you are constructing a new type of network and you want to have a comparison with what is usually done in literature. So you use these datasets that you can find online. Or the choice that is commonly used is to construct a dataset from scratch that is both pretty related with your problem. As in our case, the dataset is composed of images that we have collected in the lab of the company. So after you have all these pictures, you need to label them manually. And then you also need to create all the structure that is needed for your problem, and also to create the correct structure for your dataset in order to be used in PyTorch. After this, you need to choose the model. And here, this choice depends on the problem that you have. And also here, there are a lot of choices that are, so a lot of networks that have already been implemented. So usually, also if you are on the first steps on your project, you are not going to construct a network from scratch, but you are going to start from some of the networks that you can find online. And so here you have a list of them. So after you have the dataset and the model, what you need is to train your network. So you want that your network will learn a task, so your chosen task. And so in this case, what you're doing is you are providing some pictures and some labels, and you want that the network will be able to understand and to learn the correct association between the picture and the label. And so we'll learn how to classify the pictures. After this, you will test the network, and so you will test the accuracy of your network. So how good is the network in making predictions? And so at this point, what you are going to do is you are providing to the net some new pictures that were not part of the training data set, so were not the images that you provide to the net in the previous step, but some new pictures. And you want to test the prediction that your network will make and seeing if they are good or not. After this, you should have a network that is well performing. Otherwise, you should tune better some parameters, so repeat some steps. So after this, what you will do is to have a practical application. And in our case, this means that we need to take our network and place inside a professional appliance. And in particular, place it inside an embedded system. And here is where we have faced and we have encountered the problem of dimensionality. Because in our case, we have that our net requires like 56 megabytes of space in memory. And here I can also tell you that if you need to store also other information about the network, the space required will also increase. Whereas the space that we had available in the embedded system was only 30 megabytes. So here we have the question, so how we solve this type of problem? And the solution we have decided to follow in this case was to perform this dimensionality reduction of a convolutional neural network. And so here we have the second question. So how can we perform this reduction and construct a reduced convolutional neural network? So now we can go into deep about this topic. So first of all, we will focus on a simple problem that is that of image recognition, and then we will try to generalize everything to the problem of object detection. But we will explain you better the difference between these two problems later on. So let's start with the problem of image recognition. This problem is part of computer vision and aims at solving the problem. You have some pictures and you want to recognize the objects that are present in the pictures. So you want only to have a recognition and a classification of the objects. And convolutional neural networks are these algorithms that are able to solve this task. So they can take in input an image, they are able to assign importance to the different features of the object and differentiate them between all the objects that are present in the pictures and also between all the objects that compose your dataset. You can see here a sketch of a convolutional neural network. Obviously, I'm not going into details about how the neural networks work, but I want only you to have the idea of how it works. So you can see that here you have in input a car, so a picture of a car, and in output you have this vector, where near each component of the vector you can see that there is a label, and these labels correspond to different means of transport. So you have a car, truck, van, and so on. And in the middle you have a structure of a net that can basically be subdivided into parts. So you have the feature learning part, that is the first one, and this is responsible to detect the different features of the object. Where with the features of the object, I'm meaning exactly what you think of the features of an object. So what characterizes an object, like the shape, the color, all the details that characterize an object with respect to another. And here you are detecting these features using these boxes, and in particular using some filters that are placed on the picture and are able to solve this task. So if you use, for example, different features, different filters, you will detect also different features. I can provide you an example on how, for example, you can detect the presence of vertical lines on a picture. So you can see on the first one, a picture that is composed by a white part and a gray part. And here I've stressed a bit the black line, that is the line that is subdividing these two parts. And this is the line that we want to detect. You can see on the top of this picture, the image that corresponds in pixels. So you have that the white part corresponds to this part where you have the pixels that are greater than 0, whereas the part with 0 pixels corresponds to the gray part. Then on the middle, you have this little matrix that is called filter, that is composed of a column of 1 that is corresponds then in the picture below to the white column. Then you have a column of 0 that corresponds to the gray column, and a column of -1 that corresponds to the black column. So now what you are doing is you are performing this convolutional operation that corresponds to the mathematical convolution that you have in mind. And so in this case, what you are doing, you are taking this filter matrix, you are placing, for example, on the top of the picture, you are considering both this subpart of the picture, you are making the product component by component, and then you are summing up all the output of this product. And this will be, for example, the number that you are going to place on the top of your output matrix. But it's not so important that you understand now how I'm doing this operation. We can, in case, speak about this later. So if you see what you have in output, we have that this matrix that has the first and the last column that has values that are equal to 0, and so will correspond at the end to these columns that are gray. And in the middle, what you have these columns with values that are greater than 0, and so this corresponds to a white part. And this is telling you that the line that you want to detect is present in this white part. So this white part is telling you where you have the line, the vertical line. So now we can go back to the structure of the convolutional neural network. So after you have detected, using these filters, all the features of the object, you are going to use them in order to classify the object. And this is what is done in the classification part, where you're using a feed-forward neural network in order to obtain at the end the vector, this vector that is going to tell you the class to which your object belongs to. Because this vector is a vector of numbers between 1 and 0, where 1 is telling you that the probability that the object that is present in the picture belongs to that class is 1, and so it's certain that this is the case. Otherwise, if it's 0, it's telling you that the object does not belong to that class. As I told you before, there exists a lot of convolutional neural networks that have already been implemented in order to solve the problem of image recognition. You can find here a list like the AlexNet, the BGGNet, the ResNet, the Inception, and so on. And we will see then also the net that we have decided to use. So now that we have all these ingredients, we can move to the reduced approach that we have developed. So here you can see a scheme of it in order to understand, before going into details, the idea that we had and that is at the base of this reduced approach. So on the top, you can see the scheme of a convolutional neural network, like the one I've shown you in the previous slide. So we have started from the convolutional neural network, and what we do, we split the network into parts. So we are cutting the net at a certain layer. And those, all the layers that are before this cutoff index, so the layer in which we are cutting the net, define the pre-model, and all the layers that are placed after this cutoff index define the post-model. We are only retaining the pre-model, so the layers that are placed before the index layer where we are cutting the net. And here we have that the output of this pre-model lies in a high-dimensional space. So here is where we are performing the reduction. So we are in this way, with this reduction layer, reduced the output of the pre-model, and we are obtaining a reduced vector. After we obtain this reduced vector, we need to go back to the final output, so the classification vector, the vector of 1 and 0 that I tell you before. So what we need is to use an input-output layer in order to do this. I want also to mention that this reduced approach is part of our article, a dimensionality reduction approach for convolutional neural networks, that is present on arXiv, and I hope also will soon be published. And also I wanted to mention that this reduced approach that we have developed here is based on this article of Ozeledes, Active Subspace of Neural Networks, Structural Analysis and Universal Attacks. We have started from the idea that are present in that article, but then we have generalized what is present here. And so now I'm not going to tell you the differences, but you will understand them when I will talk to you a bit better about the reduced approach, and also I will explain you better why our approach is different from the one that is present here. So let's see some more details about this. What we do is we start by taking our convolutional neural network, and we define it as, we can see it as a function that goes from a space of dimension n0, so the dimension of our input, and goes to a space of dimension n big L, so the dimension of the output. Obviously, in this case, n big L will correspond to the number of classes that you have in your dataset. The only assumption that we are making in this case is that our network is composed of big L layers. So basically, if instead of using the network that I will tell you that we have used for the test, we are using another network, another convolutional neural network, the method should work. And also, if instead of using a convolutional neural network, we use an artificial neural network, the method is working. So for this reason, we are generalizing the method that was present in that article. Then, if we take this convolutional neural network, what we can do is describing it as a composition of function, as is described in equation 1, where each of these functions fi are describing a different and representing a different layer of the net. So a convolutional layer, a batch normalization layer, a feed-forward layer, and so on. So after we have this representation, what we can do, we can define the pre-model and the post-model. So as I told you before, we are cutting the net at a certain layer, and all the layers that are present and that characterize the network before this cutoff index define the pre-model, all the remaining layers define the post-model. And this index at which we are cutting the net is called cutoff index, and is very important because it's defining how much information we are discarding and how much information we are retaining. So for this reason, the choice of this index is very important. And usually, in our case, we have like make a trade-off between the accuracy we want to achieve from our reduced network and also the compression ratio that we want to achieve. Now that we have defined the pre-model and the post-model, and so we have rewrite and redefine our convolutional neural network as a composition of the pre-model with the post-model, what we wanted to do is to focus only on the pre-model. So we are taking an input vector x0, so that is part of a training data set, and we are taking the pre-model and computing the output, that is this xl. So here what we have, as I told you before, is that this output of the pre-model lies in a high-dimensional space. In our case, we have like 16,000 parameters. So what we need to do here is to project this vector onto a low-dimensional space. And in order to do this, we have used what I told you before, that was the reduction layer. And in particular, we have used two reduction techniques that are commonly used in the context of model order reduction. So the first one are the active subspaces. So the goal of this method is to identify the important directions in the parameter space by exploiting the gradients of a function of interest. And so in this way, we are obtaining an approximation of our original function in a low dimension. So in this case, we are taking the output of the pre-model that lies in the space of dimension n little l. And connected to this, the output of this pre-model, we have this density function rho. Then our function of interest is this function GL that is defined as described here. Also here, this definition of the function was based on what was present in the article of Ozeledes. And so it's defined as the composition with the composition of the post-model with the loss function. Here with the loss function, you can also choose the loss function that you prefer. There is not a choice that is that you have to follow. Then, starting from this, we define the uncentered covariance matrix of the gradients of this function G. And so it's defined as the average value of the inner product of the gradients of this function GL computed in vector XL with itself. And you can see in equation 6 also then the integral formulation, where we are assuming that the gradients are provided during a simulation in some way or are computed in some way. Then we have that our matrix C is a symmetric matrix, and so it admits the eigenvalue decomposition that is present in equation 7, where D is this orthogonal matrix where the columns are the normalized eigenvectors of our matrix, whereas in the matrix lambda, that is a diagonal matrix, we found all the non-negative eigenvalues. Okay, so starting from this decomposition, we are performing the following decomposition for the matrix lambda and D, where if you see, for example, the matrix D, what we are doing is grouping the first are columns in the matrix V1, and the remaining one are part of the matrix V2. So, in particular, here we have that the space that is spanned by the columns of the matrix V1 are defined the active subspace that has dimension R, where in this case the dimension of active subspace is this index R, whereas the inactive subspace is defined by the columns of the matrix V2. So, exploiting this decomposition, we can rewrite XL as written in equation 9, where we are also exploiting the fact that V is an orthogonal matrix. And so at the end, we are obtaining this vector Z and this vector tilde Z, where Z lies in a space of dimension R, so is projected into the active subspace, and so for this reason it's called active variable, whereas, as you can understand, as you may think, theta tilde lies is the inactive variable because we are projecting it into the inactive subspace. So, as you may think, in order to obtain a reduced version of our original vector XL, what we are going to do is to use this projection metric, V1, in order to project it into a low-dimensional space of dimension R. So in order to give you a graphical idea of the active subspaces, we can see these pictures that are taken from this article, Athena, Advanced Techniques for High-Dimensional Parameter Spaces to Enhance Numerical Analysis, this article of Francesco and Marco. And you can see so that at the beginning, on the top, you have this 7-dimensional function. And what we are basically do with the active subspaces that we are finding the important directions of the space. And so at the end, we are making a rotation of the input domain. And so at the end, what we obtain is that we have a parabolic function that is of dimension, is scattered by dimension dimension that is less than the one of the beginning. And so it's also more easy to handle. In order to compute the active subspace, in this case, we have faced some problem because, as I told you, we have an input parameter, a parameter in input that were 16,000 dimension. So what we have used, also based on what was done in the article of Oseledes, is to use this technique that is called the frequent interaction method, that we have then implemented also inside Athena. That is this Python library that was developed, been developed inside the MATLAB group. So, since it's computationally expensive to compute C, we are now going to define this matrix G and to focus on it. And this matrix is defined with the gradients of the function GL evaluated on each sample of our training data set. So we are taking sample of the training data set and computing the output of the pre-model, and then we are constructing this matrix G. And here we can compute the singular value decomposition. So basically what we are doing here is that we are approximating the eigenvectors of our matrix C with the left singular vectors of G, so of the vector contained in the matrix V hat, and then the eigenvalues of C are approximated with the square of the singular values of G. But in practice, what we are doing is this. So in order to compute the matrix V hats that will be obviously our projection metric, we are going to select, because obviously, as I told you, we have a problem with dimensionality. So also store the matrix G will computationally expensive for us. So what we have done, we have taken our samples of the data set, so this XL, and based on this, we are constructing a reduced version of the matrix G. Then for all the remaining samples of the data set, we are going to do the steps that are present in step 3. So we are computing the S2D of the reduced metric G. Then we are updating this matrix as presented here. So we are using this matrix V1 hat that we have obtained from the S2D decomposition, and we are taking the product between this matrix and the square root of the sigma 1 hat matrix square minus this value, the square of this value sigma hat R. Okay, here we miss identity matrix. Okay, so in this way, we obtain that the last column of our matrix G red is 0. And then in the next step, what we are doing is we are taking a new sample, and then we are substituting the last column of the matrix G red, that now is 0, with the gradient of the function GL evaluated in this new sample. Then, so after you have done all these steps for all the samples that are remaining in your data set, at the end, the matrix that you are obtaining, this matrix C1 hat, is your projection matrix, so the matrix that we have also seen before. Now we can move on to the second method, second reduced method that we have, reduction method that we have used, that is the proper orthogonal decomposition. So in this case, we are taking all the samples that compose our data set, and we are performing, we are applying to them the pre-model. So we are obtaining all the output of the pre-model, and we are placing it in this matrix S. It corresponds to matrix of snapshots. So in this case, we want to describe them, all the columns of this matrix, as a linear combination of few structures that are the Pumidi modes. And those we are projecting them onto low-dimensional space that is spanned by these modes. So in order to do this, in this case, we are taking the matrix S and we are computing the singular value decomposition, where the matrix C contains the left singular vectors and those the Pumidi modes. Whereas in the matrix sigma, that is the diagonal matrix, here we will have the singular values. So now we are going to select only the first modes. In this way, we are retaining only the most energetic ones, and so the most important. And starting so from these first modes, we will construct this matrix CR, that is our reduced matrix, and that will be used in order to project the high fidelity solution into our reduced space. And so also here you can see in equation 13 how we can obtain our reduced solution Z by exploiting this projection matrix. So now that we have obtained, using one of the technique, the reduced vector, what we need to do is to perform the input-output mapping, and so go back to the final output. So here we have also used two different techniques. The first one is the polynomial scout expansion technique. So you start by taking your network, taking an input data, and see the true response of a model that is called Y. And what you want to do is to approximate this, the final output of the network as described in equation 14. So as this sum of this product of this multivariate polynomial phi alpha with these coefficients. These multivariate polynomials are chosen based on the density function that we have associated with our vector Z. So a common choice is to use, for example, the Gaussian distribution connected, and so we will have connected to it the Hermite polynomials, but there are a list of density functions that you can use, and so polynomials that you can associate with them. So after this, in order to complete this approximation, we have a polynomials. What we missed are the coefficients. So in order to find and determine these coefficients, we need to solve this minimization problem. So we are now going to minimize this square of the difference between our true response of a network and this approximation. In this way, we are going to find these coefficients, and thus we are obtaining our final output. The second technique that we have used is a feed-forward neural network. And this is also in analogy with what is usually done inside a convolutional neural network, because if you remember what I've told you at the beginning, the last part of a convolutional neural network is a feed-forward neural network. So here you can see a scheme of a feed-forward neural network. In particular, I've used only one hidden layer because also in our test we have used feed-forward neural networks with one hidden layer. So in this case, in order to obtain the final output, so this vector y hat, what we need is to perform what is done in question 16. So the final output is obtained as a weighted sum of the input coming from the previous layer, but in this case is hidden layer 1. And then we can rewrite the input that is coming from the hidden layer 1, that are this Z1, as the weighted sum of the input coming from the previous layer, and so from the input layer. And both we are obtaining this formula, where I want also to mention that as activation function, here, this sigma, we have used the soft plus function, and not, for example, the ReLU or the hyperbolic tangent that are commonly used, also because we have seen by testing these different activation functions that this was performing better in our case. Also, the loss was decreasing faster. I want also to mention that for these two methods, so for the polynomial cluster expansion and the feed-forward neural network, we are going to have a training when we are initializing these parts. So before the training of the whole network, we are training this last classification part. And so now we can move to the results. And so as a network, in order to test our method, we have decided to use the VGG16, that is depicted here. Then as datasets, we have used two different datasets. The first one is the CFARTEN dataset, that is a dataset that is commonly used in the context of image recognition, and is commonly also used in literature. And so this was used in order to have a comparison with what is usually used in literature. It's made of 16,000 images, and that are subdivided in 10 overlapping classes that are listed here. And then we have used also a custom dataset, that is the one that we have, that was provided us by the company. And so this is composed of 3,000 images that are organized in 4 different classes. So we have 3 non-overlapping classes, and one that is mixed, so contains objects that belongs to different categories at the same time. Then I want also to mention that for, as I told you, for the feed-forward neural network, we have used in both cases a feed-forward neural network with only one hidden layer. And in particular, we have used 50 input neurons in both cases because as dimension of the reduced space, so as in the case of the active subspace, in the case of POD, at dimension of the projection matrix, and so of the reduced vector, we have used 50, where this 50 is not a value that we have chosen randomly, but was based on the article of Ozeledets. And here there was also eigenvalue analysis that was telling us that this was the correct value. And then also for the structure of the feed-forward neural network, we have not chosen it randomly, but we have tested the different architectures, and we have seen that this was the one that was performing better for our case. Now we can see also the results that we have obtained. Here you can find both the one for the CIFAR10 and the custom dataset. Let's start from the one that we have obtained from the CIFAR10 dataset, and then we can see that they are consistent also in the custom one. So on the top, you are going to see the results and what we have obtained with the full network of AGG16. So after a training of 60 epochs, we have obtained a net that has a 78% of accuracy and require 56 megabyte of space. Then you have a list of all the reduced network we have tested. So you can see that there are 3 different indexes, 5, 6, and 7, and this represents the different cutoff indexes that we have used. And then for each index, you can see that there are 3 reduced networks. And this represents all the choices that we have decided to use. The first one combines the active subspace with the polynomial self-expansion. And this is the choice that was present also in the article of Oseledes. Okay, so we have starting from the same choice that they have made. And then starting from this, we have generalized everything using other possibilities. So there is the choice of the active subspace plus the feed-forward neural network, and the choice of the POD plus the feed-forward neural network. We can concentrate, for example, to index 6. And you can see here that at epoch 0, with epoch 0, I'm meaning the status of the net after we have initialized it. So we have not trained the network at all. So you can see that for the POD plus the feed-forward neural network, after only the initialization, we have a reduced network that is well performing. Okay, 64% is not a high accuracy, but for some cases it can be good. And then if you see, for example, index 7, the accuracy increase. Then after the training, you can see also that, so after 10 epochs of training, you can see that we obtain reduced networks that are all well performing as the original one. And you can also see then that the space that is required by our reduced networks in all the cases is less than 8 megabytes. So we were able to have a reduction of 90% of the space that is required for our network. And in particular, you can also see that for the case of feed-forward neural network or polynomial expansion, the use of a feed-forward neural network is also providing a decreasing of space required of 2 order of magnitudes. Then there is also placed here the time that is needed for initializing the networks and training. And the important thing here is that, for example, if we are using the POD plus the feed-forward neural network, and we are obtaining after the initialization already a well-performing network, we are saving also this 5-hour training. So we are saving also this time that we need for training. You can then see that using a custom data set is not changing what we are obtaining, and so it's consistent. And because you see that in all the cases, we have at the end a network that are performing as well as the original one, and requires a 90% of space. Require the 90%, no, the 10% of space, okay. And so we are saving the space that we have, and so we are solving the problem of that we're connected with our space in memory. So after we have seen this for the problem of image recognition, we can try to understand what happens with the problem of object detection. And so the problem of object detection is different from the problem of image recognition, because you don't only need to classify the objects that are present in the picture, but as I told you at the beginning, you want only to draw you want also to draw these boxes around each object in order to localize them. And so you want to localize the object and classify the objects that are present in that only in that region of the image. And so, in order to solve this task, the architecture that are able to solve this task are this object detector that differ from the simple convolutional neural network because you start from it and then you are adding some additional structures that will detect and will be responsible for the detection of the position and also the creation of these bounding boxes. So also here there exists a lot of object detectors that have already been implemented in order to solve this problem. And some of them are listed here. So we have SSD, FASTER, RCNN, the YOLO, and so on. We have concentrate on the SSD 300 or object detectors that are characterized by a structure that is similar to this. So architectures that are mainly based on a base net, that is the classical convolutional neural network that we have seen before. Then you have some auxiliary layers that will be responsible to detect the high-level features, so the features that are connected with the position of the object and the object on his whole. And then you have a predictor part that will be responsible to give you the classification of the object, but also the localization. And so let's see a scheme of our method. So as before, on the top, we have the scheme of our object detector that, as I told you, is composed of this base net, this followed by these auxiliary layers, and then you have the predictor. And here you can see that the input for the predictor part is not only the output from the last auxiliary layers, but the inputs in this case are the output from each of these auxiliary layers and also the output of the base net. So starting from this, we are trying to apply the method that I've described before, so our reduced approach. So also here we have a base net that is a convolutional neural network as before. So we are splitting the network in two parts, and we are retaining only the pre-model, so only the first part. Then also here, the output of the pre-model lies in a high-dimensional space, but in this case was also bigger than before, because for this type of network, you need images that have more pixels. So in this case, for example, we have images that are 300 times 300 pixels. Before we have images that were 32 times 32. So you can understand that obviously we will have more parameters. I think that we're like 40,000. Then after you have this, you are performing the reduction. Okay. In this case, we have used only the POD because we have seen before that it was performing better. Okay. And so at the end, also in this case, we have a reduced vector. And this will one of the input of the predictor part. But obviously, as we have seen on the top, the input for the predictor part are a lot. So in this case, we have tried to use as input not only the output of the reduction layer, but also the output of the pre-model, and try to see if everything works. In this case, as predictor, we have retained and we have maintained the classical structure that was present in the SSD. Also, this reduced approach is present in this article that we have just finished, a proprietary decomposition approach for parameters reduction of single-shot detector networks that we have submitted, and I hope also that we'll accept it. And it's true. And will also soon be available on archive. So if you're interested, you will find it soon. So let's see the beautiful results that we have. So I want to mention before that for the image recognition part, we have taken our full network, the VGG, okay? We have trained it, and after this, we have constructed the reduced networks. In this case, we are doing something different because we are taking the full network, the SSD300, okay? We have trained it. And then, in order to construct the reduced version, okay, at the first step, we have constructed the reduced version of a net starting from the trained one. But then we have seen something interesting, and so we have taken the network after only the initialization step, where all the weights, so if you see here, all the weights are randomly chosen. Only the weights that are placed in the base net are initialized, because usually what you do, you take as weights for the base net, not some random weights, but you are taken some pre-trained weights that you can find on PyTorch, and so they are pre-trained on a big data set. It's called ImageNet and is commonly used in this context. And so starting from this, we have constructed the reduced approach. And we have constructed the reduced version of the net. So you can see that. In particular, I want also to mention that in this case, as a dataset, we have used a dataset that we have extracted from the Pascal VOC, because using the whole dataset Pascal VOC was computationally expensive for us, so we have extracted only a dataset that will consist of 600 images that were subdivided into classes, cats and dogs, as you can see here. So if you see from the table, you can see that you can see this index that is called MAP, that is mean average precision, that is taking the mean of the precision that you obtain with the two different classes. And so you can see that with the whole network, we have an accuracy of 70%, whereas with the reduced version, we have an accuracy of 59%. So we are losing like 10% of accuracy. But if you see the pictures, you can understand that the network is performing well, because if you see the output from the SST300 and from the reduced version, you can see that both the networks are able to draw the box around the different animals, and also to label them correctly. Then you can see from the point of view of storage that we are decreasing the space that is required of only 13%. So we don't have a high gain as before, but we have already some ideas on how we can improve this. And then the last interesting thing is the training time. So I was telling you about how we have constructed the reduced version for this fact, because for the whole network, we need like 44 hours in order to have a training of 500 epochs. Whereas with our reduced version, we only need 26 hours for a training of, also in this case, 500 epochs. So we were able to obtain a network that require half of the time of a full network. And so also here we have an improve by using our reduced approach. I want also to mention that also here we have tested everything with our custom data set that we have collected in the company, but since there is some NDA, I can't show you this picture, so we have cats and dogs. So now we can conclude. So in order to summarize a bit, I've presented you a reduced approach for artificial neural networks that was able to solve the problem that we have seen at the beginning of the storage in memory of our convolutional neural network. We were able to obtain networks that are reduced but have the same level of accuracy as before, and we were also able to speed up the training process. What can we do in the future? We can try, for example, to have an iterative procedure that converges to the optimal structure of our reduced network. For example, because now we are determining the cutoff index manually. So we are making this trade-off. That means that we are trying and see what happens. Maybe in this way we can skip this thing and have an iterative method that gives us the best index. Then, as I told you before, we already have some ideas on how we can have a better reduction for the case of object detection. So we can use some variants of the POD of a reduction technique in order also to minimize the quantity of data that has to be saved. And then we are also working on this construction of a continuous version of the discrete filter that characterize a convolutional neural network, in order also to have an application to other contexts. And this is the work that we are doing with Dario Coscia. And obviously, last but not least, I have to write my PhD thesis. So thank you for your attention, and if there are questions, I'm here.
If also the online audience wants to do a question, they can unmute themselves. Just a curiosity in the meantime. Have you tried also comparing your results with other techniques, more standard like pruning and teacher-student training?
We have started also from them. We have seen what was done in literature, and we have seen that also this was also described in that article of Ozeledes, that these techniques works well, but they have some limitations. For example, connected with computational things or so on. And so for this reason, they have also shown that using this type of approach instead of the common techniques that are known is better. But basically, the idea that is behind is quite the same. So you are like taking some things instead of others, but this is working better.
If there are no other questions, let's thank Laura again.
Thank you. Adesso aspetto che sistemi